So the first question says a 60 Hz 4-pole turbo generator rated 100 MVA, that is a 60 Hz 4-pole turbo generator rated 100 MVA and 13.8 kV has an inertia constant of 10 megajoules per MVA. What is the notation for inertia constant?
H.
Yeah, 10 megajoules per MVA. Now, the first part of the question is find the stored energy in the rotor at synchronous speed. Stored energy in the rotor at synchronous speed. Okay. How will you find it? Stored energy equals GH. Yeah. So what is G here?
100 MVA.
100 MVA. Okay. So this is 100 MVA. Then what is H?
10
MVA.
10 megajoules per MVA. Right. So stored energy equals 1000 megajoules. Okay, 1000 megajoules. Now, in the second part of the question, let me take, okay. In the second part of the question, if this rotor acceleration is maintained for 12 cycles, find the change in torque angle and rotor speed in RPM. So if this rotor acceleration is maintained for how many cycles? 12 cycles. Okay, so everything we need to convert in terms of time. So 12 cycles we need to convert to time. Okay, that we'll do. Now find the change in torque angle. What is change in torque angle? It is delta del. Okay, change in torque angle is delta del. Then rotor speed in RPM. You are asked to find the rotor speed in RPM also. Now at the end of this period, at the end of this period, in the sense after this 12 cycles, what is the change in speed and change in torque angle? Okay, now how to find the acceleration? What is PA? Accelerating power PA. PA is equal to PM minus PE equals M d squared del by dt squared. Right. Now, how will you find M? What is M?
H upon pi f.
GH upon
In per unit. Yes.
180F. Right. See, if it is 180F, then the unit will be megajoules second per electrical degree. Otherwise, it is megajoules second per electrical radian. So I have taken it as 180 instead of pi. So the unit will be megajoules second per electrical degree. So now what is GH? GH is 1000, right?
Yes.
GH is 1000 divided by 180 into 60 Hertz is given. So this is 60. What's the value? Can somebody find?
0.0925.
0.09?
0925, sir.
Okay, 0.0925. You check it whether it is 5 by 54. I am getting here 5 by 54. 0.0925 megajoules second per electrical degree. Okay, electrical degree. Now your M d squared del by dt squared equals PM minus PE. Right. So d squared del by dt squared. How will you find d squared del by dt squared? D squared del by dt squared. What is PA here? What is PA? This one, PA. What is PA? In the question, it is, say, if the input to the generator is suddenly raised to 60 megawatts from an electrical load of 50 megawatts. If that is a condition given, if the input to the generator is suddenly raised to 60 megawatts from an electrical load of 50 megawatts, then what is PA?
10.
10. Yeah. So this is 10, right? 10 megawatts. So this m d squared del by dt squared, you know that because m you have evaluated here. Now you need to find d squared del by dt squared, which is the acceleration. This is the acceleration. Acceleration. Can you find it? What's the value? So whatever you have obtained as m is
108.108.
Yeah, 108. Approximately I'm giving it 108. Okay, I'm taking it as 108. 108 electrical degree per second squared. Okay. Now, the third part of the question. In the third part of the question, if this rotor acceleration is maintained for, okay, that is the third part of the question. Okay, actually, second part of the question asks rotor acceleration, and then in the third part of the question, if this rotor acceleration is maintained for 12 cycles, find the change in torque angle and rotor speed in RPM at the end of this period. So the acceleration which has to be maintained is this 108 electrical degree per second squared. Okay, so if this is maintained for 12 cycles, what is the time corresponding to 12 cycles in a 60 Hertz system? 12 cycles divided by 60, right, is equal to 0.2 seconds. So after 0.2 seconds, what is a change in del? We have to find. That means delta del equals, actually it is ut plus half at squared plus, but u is 0, so I am taking here this as half a into delta t squared. Okay, now what is a? Half into, what is a?
108, sir.
108. So this one here, right? So 108 half into 108 into delta t squared. What is delta t?
0.2, sir.
Yeah, initially it is 0 means 0.2 minus 0, right? So this is 0, 0.2 squared. So what is the value for delta del?
.16, sir.
Yeah, 2.16 electrical degree, because we have taken everything in terms of degree only. Okay, now let's note something here. 360 degree equals 1 revolution, right? What about 1 degree? How many revolutions?
1 by 360.
360 revolutions, right? Now what about 108 degree? Whatever we have obtained here is here 108 electrical degree per second squared, right? So what about 108 electrical degree? Equals 108 divided by 360 revolutions, right? Because slowly we are moving to RPM, right? Now from degree slowly we are moving to RPM. So RPM or RPS, if you know RPS, then you can find RPM. So 108 divided by 360 revolutions. Now we have 108 electrical degree per second squared, which is equal to 108 by 360 revolutions per second squared, right? Revolutions per second squared, which means if you are going to convert this to revolutions per minute per second, then 108 divided by 360 into 60. Then 1 second will convert to minute. Here 2 seconds are there, right? Second squared is there. So 1 second will be converted to minutes. So this will be revolutions per minute per second. So what is this revolutions per minute? This is RPM. Right. So 18. This is a 18. Okay, 6. I think this is 18, right?
Yes, sir. Yes, sir.
Yes,
18.
18. So 18 RPM per second. 18 RPM per second. So now what we are going to do is rotor speed at the end of 12 cycles. You need to find rotor speed at the end of 12 cycles. How will you find it? How will you find it? Suppose V equals U plus AT. This is for linear. Corresponding
Omega equals to
if you're
omega
taking,
naught plus alpha t.
yeah, omega equals omega naught plus alpha t. What is alpha here?
Angular accelerations.
What is angular acceleration here? In terms of RPM, you can take it as RPM.
18.
18. So this omega, this is omega naught. Omega naught is 120 f by p because initially it is running at synchronous speed plus alpha into delta t. What is delta t?
0.2.
0.2 second.
0.2. This is 0.2. Okay, this is 0.2. 1 minute. Okay, this is 0.2. Then what's the answer? Can you calculate it? 120 f by p. What is 120 f by p here? 120 into 60 divided by 4
1800.
plus 18 into 0.2. The whole thing is your omega. Omega is in RPM now. We have converted it. So what is the answer?
1803.6.
1803.6 RPM. Okay, so this is what we get for the question 1. Now let's move on to question number 2. A 400 MVA synchronous machine has 400 MVA synchronous machine has H1 equals 4.6 megajoules per MVA and a 1200 MVA machine, a second machine, 1200 MVA machine has H2 equals 3 megajoules per MVA. The two machines operate in parallel in a power plant. Okay, find out the H equivalent relative to a 100 MVA base. Find H equivalent at 100 MVA base.
So
how will you find this?
54.4.
How will you find this? Yes, 54.4 is the answer. How will you find it?
G1 H1 plus G2 H2 upon H
G1
system.
H1 plus G2 H2 upon G system.
G system.
Right. So this is 4.6 into 400 plus 3 into 1200 divided by 100 MVA base, right? 100 MVA, which is equal to 54.4 megajoules per MVA. Okay. Now a 100 MVA 2-pole, 100 MVA 2-pole, 50 Hertz generator has a moment of inertia. What is moment of inertia?
H.
What is moment of inertia?
J.
40 into 10 cube kilogram meter squared. Okay, this is your J. Okay, J. Then what is the energy stored in the rotor at the rated speed, and what is the corresponding angular momentum? So two things are asked. First one is energy stored at rated speed. Second one is angular momentum. And third one is inertia constant, that is H. Okay, inertia constant, that is H. Now, how will you find the stored kinetic energy?
Half J omega square, sir.
Yeah, stored kinetic energy equals half J omega squared. Right. This is mechanical speed only, omega m. So this is equal to half into J is 40 into 10 raised to 3. Right. 10 raised to 3 into, how will you find omega m?
So 120 F by P.
120 F by P is, can you calculate it? 120 F by P. 120 into 50 divided by 2, which is equal to 3000. Unit is RPM. Okay, this is RPM. Now, this omega m. What do you need to do now?
2 pi n by 60.
2 pi n by 60. So n is here 3000, right? So 3000 into 2 pi divided by 60 squared, right? Squared. Now, if you want to change it to megajoules, convert it to megajoules, then 10 raised to minus 6 megajoules. Okay, megajoules. Somebody's voice is breaking. Can you repeat?
The frequency is 50 hertz, sir.
Question, it's 50 hertz, right?
Yes, sir.
This is what 50 hertz is taken, right? Here.
No, sir. 60 is there.
That is 6 seconds, sir. That is correct.
This is current, right? This one.
Correct only, sir.
50
I mean,
hertz. Yeah. Okay. Now, what's the answer for this one? Stored kinetic energy?
1960 megajoule.
19. I don't know. I'm getting here 1974. Maybe wrong, but you can calculate it. Half into 40 into 10 raised to 3. Can somebody recheck it? You can check it.
Yes, 1971.
Oh, okay, maybe 1971. Okay. Now, what's the second part of the question? Angular momentum is asked, right? How will you find it?
So might be J omega.
J omega.
J into omega.
J into omega m, which is equal to, again, this one. This is J, right? J into omega m is same, 2 pi into 3000 by 60. 2 pi into 3000 by 60. Into 10 raised to minus 6 means, what is the unit? Megajoules second per mechanical radian. Okay, mechanical radian. I think this is 12.568 megajoules second per mechanical radian. Okay, so these are the 3 questions from the lecture 5.1. Okay, yeah, tell me.
So is angular momentum denoted by m, or that is just a constant, right? M that we have used previously.
No, actually here I have taken it as m. That's all. I think you are referring to m d squared del by dt squared, right?
Yeah, yes, sir, right.
No,
So that
here
is
I have-
moment of inertia constant.
that is what this is. Okay, let me change it then. Okay, angular momentum. I'll write it as angular momentum itself. Okay, angular momentum. Okay, don't mistake. Okay. Now, have you gone through the active and reactive power flow modeling? I mean equations.
Yes, sir.
Yes, sir.
Last lecture.
Yes, sir.
Okay.
Yes.
Now we can go for the last question. The sending end and receiving end voltages of a three-phase transmission line at a 200 megawatt load, 200 megawatt loading. Okay. Sending end and receiving end both are equal to VR equal to 230 kV. Okay, sending end and receiving end voltages of a three-phase transmission line at a 200 megawatts load are equal to 230 kV. The per phase line impedance is per phase line impedance equals J14 ohms. Okay, calculate the maximum steady state power that can be transmitted over the line. How will you find the maximum steady state power? See, steady state power, active steady state power is mod Vs into mod Vr by X sin del, right? If Vs is the sending end voltage and Vr is the receiving end voltage, we have already seen that it's mod Vs mod Vr by X line into sin del. When del is 90 degree, it's maximum, right? Maximum power is transferred from the sending end to the receiving end. Here Vs equals Vr. Vs equals Vr equals 230. If you want per phase, then divided by √3, which is equal to 132.79 kV. Okay. Now the PR max or PS max, that means maximum power that is transferred. So P transferred max equals mod Vs into mod Vr by X. So this is 132.79, both are same. So 132.79 squared divided by what is X? J14, it is given, right? 14. So can you find the answer?
3,778.57.
132.79 squared divided by 14. I don't know. Now we have converted to per phase, right? I don't think the value. Let me see then.
So 3,778.57.
3778 point.
78.
That is three phase, right?
Yes, sir.
That is three phase. Okay, so per phase is 1260, I think. 1260 megawatt per phase. Now when this is multiplied by 3, right? 3 into this one, 1260 megawatts per phase equals a three phase power, which is somewhere around 3779 megawatts. Okay. Now, so this is what. Now, from the next lecture onwards, we'll start with equal area criteria. So I'll post it.